And hi there. Now, as I mentioned in the previous video, these radicals tend to cause problems for students. So I'm going to work a lot of examples and try to come up with different scenarios so that you'll have something to look at. So when I go to solve something like the square root of 50, this is the square root. So I'm looking for things in pairs. I try to think of what's a perfect number inside of 50. And I see that 25 because 5 times 5 is 25. But it's not just a 25, it's a 50. So if I had 5 times 5 times 2, that is my 50. I can only take out things that came in pairs. So that means I can take this 5 out, but that square root of 2 is still left in there. And we say that 5 square roots of 2, and what it really means is 5 times the square root of 2. And it's just a number. Square root of 2 is just 1.414, and it's a decimal approximation, but it is still just a number. So don't let him scare you. So if I look at 24, I'm going to say, oh, what's inside that 24? So let's break it apart into some factors. I see that there is a 4 times a 6, but that's not a pair. Oh, but 4 is a perfect number. When he comes out, he's a 2 because he really looks like 2 times 2 times 6. And that 2 can come out. He's a 4, and he comes out as a 2 with that square root of 6 still left in there because there's no pairs in a 6. Let's move on. So this one has numbers and it has variables. We need to do each of these independently. And if I were to do the 48, let's see, 48, that's a 6 times 8. Oh, there's some 4s in there. Let's see, I see that there is 4 times 12 in there. That 4 is perfect. He does come out. When he comes out, he is a 2. So I'm going to write this down. And then I've got a 12 left in there. But you know what? I'm not done because I see a 4 inside that 12 and he's perfect. But that's okay. I can get him in just a minute. I can keep whittling him down. Let's look at these x's. I have 3 x's. I can take out this pair. When I do, that's just an x, and then there's one x left in there. The y, there's 4 of those. 3, 4. I take them out as pairs. So when I take those out, that is y squared, because it's a y times a y, with nothing left in there. So I'm pretty close. I just need to do something with this 12, because that 12 is basically a 4 times a 3. And that 4 can come out. When that 4 goes out, he is then a 2. He'll combine with this 2 right here, and 2 times 2 is 4. So he's out of there. And these guys stay the same. And what's left is that 3 and that lonely x. And that's your answer. It's an ugly answer, but it is still the answer. So let's move on to this next one. Got a lot going on this one. Might even need more room. So I see that that's 4 times 10 because 4 is a perfect number. 4 can come out. When he does, he is then a 2. Let's see what we have left. Oops, I should have left myself more room. Let me do this because I'll need room for those other letters. That 10 is still left in here, so I'll write him down. Now, a squared. He's perfect. He comes out as just an a with nothing left over. So that's a times a. He's perfect. B to the 10th. I could say that that's b to the 5th times b to the 5th. That's another way to look at it. That's a pair. And it comes out as b to the 5th. That's c to the 5th. So I could say that that's c squared times c. There's me a pair. Comes out. Your c squared when you're out here, and then just 1 left in there. And that's all there is to that one. All right, let's look at a bunch more. All right, we need to do some cubic roots. And for the most part, when you're working with these problems from here on out, you'll do mostly square roots. There'll be a few random cube roots, but and they'll make you do fourth and fifth roots in this class, but really the most useful things for you later on are going to be square roots and cube roots. So be sure and focus, make sure you can get both of those. Same thing that I did before, but this time instead of pairs, I'm looking for triplets. So I start looking at 16, and I see that 16 happens to be 2 times 2 times 2 times 2. That is a 16. I can only take out things as triplets, so this guy can come out. He comes out, so I need to keep my 3 in there. He comes out as a 2 with a 2 left over. And that's another way to write the cube root of 16, and that's simplified there. Let's look at this guy. So let's start breaking him down. 250 can be thought as 5 times 5 times 5 times, because that's 125, times 2. I take out things as triplets, so this 5 comes out, and I have 5 onto the cubed root of 2. And that's all for that one. All right, let's look at this guy. Let's put some x's and y's in there. Remember, I do the x's and y's separately than I do the numbers. So I'm going to look at 64. I'm going to break him apart. I've done these before, so I happen to know that 4 times 4 times 4 is a 64. If you don't, that's okay. You'll just be messing around with 2's for a while, but you should end up with the same answer that I get. Whoops, I didn't mean to do that. Because you're going to be taking out this 4, because that is 64, and the cube root of 64 is a 4. Let's leave myself some room. That way I can write whatever's left, but he comes out evenly, so there's no numbers left in there. X to the 5th. I'm looking for things as triplets. Remember, one thing I could do is just say how many triplets, how many groups of 3 are there? 5 divided by 3. Well, there's 1 with 2 left over. Let's look at that. See how there is 1 group of 3, x, with 2 left over. So that would be x squared. Y to the 6 comes out evenly, so that y to the 6 comes out as y squared. Put it right there. And z, there's 1 group of 3 there, and that's it. So z cubed can come out as well. And he's just plain old z, so all we had left in there was just that little old x squared. All right, let's move on. Got to do numbers and letters separate. 54. Oh, let's see. How about 2 times 27? That's how you'd break apart. And 27 happens to be 3 times 3 times 3, I think. Yep, because 3 times 3 is 9, times 3 again is 27, times 2 is 54. Okay, so let's do my numbers. Triplets can come out. So the 3 is let loose out of that jail. He's no longer in that cube root prison, but the 2 stays in that prison. A squared, honey, you're going to have to stay. There's no triplets in you. B cubed, now you get to come out because you're a whole triplet. So you're just a B when you come out of there. C to the 4th, you're actually a C cubed times a C to the 1st. That's C to the 4th. You can come on out because you're a triplet. And then there's 1 more C left in there. And there we are doing some cubics. Cube roots, actually. Cube root, guys. All right, let's look and see how these might simplify. You know, you can rewrite this as the square root of 1 over the square root of 2. Now, mathematicians hate square roots in the denominator, and what this really is 1 over the square root of 2. They can't stand that. They just won't have it. So you have to get the square root out of the denominator, and it's kind of like getting a common denominator, if you will. The way to get this square root out of the bottom is to multiply top and bottom by the square root of 2. Now, what you will end up with is 1 times the square root of 2, which is the square root of 2. And then this little trick makes it so that you have 2 times 2 in the denominator, which is a 4. Well, we pulled that little trick on purpose because what is the square root of 4? Why, that is just a 2, my friends. So there's what we have left. Let's play again. This is really the square root of 5 over the square root of 6. Mathematicians don't like square roots in the denominator, so we have to get it out of there. We call this rationalizing a denominator. So that's what it's called. It's called rationalizing. Rationalizing a denominator when you get the square root out of the bottom. Same deal again. I'll pull this little trick because I know that when I multiply top and bottom by the square root of 6, I'll get square root of 36 here in the bottom. And that's just going to be a 6. And that's cool. Up here on top, I'm going to have the square root of 30. And I don't believe there's a perfect number in there. Perfect numbers, let's see. They would be 4, a 9, 16, 25. None of those numbers are factors of 30. So you just stay there, little bud. You're done. Let's look at this guy. Same thing. Oh, I'm going to multiply top and bottom by the square root of 6 because we don't like that square root in the bottom. It's just something about it that drives mathematicians crazy. So we're going to make sure that we get it out of there. And we're going to have the square root of 36, which is then going to be a 6. So I'm just going to write it like that. And then we have 4 onto the square root of 6. Now, if you will look at this 4 and this 6, notice how they're both outside of that jail. So they can cancel. I can't go inside the jail because the 4 and the 6 don't associate with anyone in those kind of radical prisons. So I'm going to look at that 4 over 6 and I'm going to say, you know what, there's a 2 in both of you dudes, and you're a 2 and you're now a 3 when I do my reducing. So this reduces to 2 under the square root of 6 over 3. This is as low as it will go because the 2 and the 3 are reduced as low as they can, and nothing can go inside that prison unless they happen to be in the prison already. If I would have had something like the square root of 6 over the square root of 3, and that could be written as the square root of 6 over 3, and I could have said that that was the square root of 2. Notice that they're both in the prison. That's why we can do some little manipulation there. That's not what we have here. In this one, the 3 is outside the prison, the 2 is outside the prison, so then they can't associate with anybody inside that radical prison. All right, let's get some more problems. All right, let's look at this guy. What a mess. Okay, so I'm going to look at the top and the bottom, break this apart. You're 12, x to the 5th, y to the 3rd. I'll look at you, and I'll also look at the square root of 5z. A lot to do here. I can look at maybe rationalizing the denominator first, or I can look at this numerator and see that there's stuff inside of here that can be reduced. It doesn't really matter which way you go first. I'm going to choose to deal with the numerator first. It's just the way I want to play, but you could choose to do the denominator and rationalizing first. Doesn't really matter. So I'm going to look at that 12 as a 4 times a 3. I'm going to look at that x to the 5th as basically x squared times an x. That's my x to the 5th. And the y cubed, I'm going to look at him as y times y times y. Because what that means is the 4 is going to come out. He's going to be let me get my line in there. 5z. Got to get all that stuff in there. So he's going to come out, and I'm going to have a 2, and then the 3 is going to be left. For the x value, this x squared, he's going to come out. He's going to be an x squared because I use a pair, and that one x is left. Here's another pair, just a plain y with one of those y's left in there. So this is what I have so far. So far that numerator is done. He's simplified as low as he can go. But you know that denominator still has a radical in it. So I've got to get rid of it. So I'm going to multiply top and bottom here by the square root of 5z. What a long problem. And what I've got when I do that is, let's see, everything on the outside stays. And then I'm multiplying everything that's inside the jail. They can all congregate. So I've got a 15 in there. I've got an x, I've got a y, and I have a z. 15 is as low as he'll go. He won't go any further. And then in the bottom here, I have 5z. I look to see if anything cancels there on the outside. Nothing does. So he is complete and a mess. I know. Sorry. All right, let's look at this bad boy. I've got the cube root of 2 in the bottom. Now, I don't want those on there. I don't want a cube root of 2 in the bottom. But if I multiply top and bottom by this, it doesn't really get me a perfect cube in the bottom, because what this would get me is the cube root of 4, and that's not perfect. But the cube root of 8 is perfect. The cube root, if I multiply, I would end up with the cubed root of 8 down here. And my whole goal is to get that radical out of the denominator. So that would get me the cube root of 8 down there, and that is a 2. So that would work for me. So what I get with this is 8 onto the cube root of 4, because I had to use 2 of those things, which was a little tricky. So when you have a cube root in the denominator, they're a little trickier. What do I have left? You're now a 2. See how that radical just went out of the denominator? Nice. Now I'm stuck with you. Look at these two guys are out of the jail, and they do simplify. 2 goes into 8 4 times. So what you're left with here is then 4 onto the cube root of 4. And that is your final answer. All right, we have one last type of problem to show you. And we've been doing these square roots, and basically we've been kind of cheating when we do it in the problems. They will either say, do not assume the variables are positive numbers, or do assume that the variables are positive numbers. Well, we've been doing the problems where we assumed they were positive, and then we didn't have to deal with x or y or z or a, b, whatever, being negative. But now let's open up the whole playing field. Let's say that x and y could be negative. Well, what happens if I have, let's say, a negative underneath the square root? Well, what happens with a negative underneath the square root is it's not real. So if I were to have, let's say, a negative 16 under here, that would be one where I'd say, well, that's not a real number. And that's a case that I really haven't considered until this point. So what we do when they can be anything is we say, well, our answer, we need to eliminate any negatives that we say could come out. And how we'll do that is we'll do our numbers just as normal. That'd be 4 times 3. The 4 comes out as a 2. Leave myself some space with the 3 left in there. For this x squared, when he comes out, in order to show that he can't be negative outside there, I just do this, because that makes that answer positive no matter what. And the y, because there's 3 of these y's, he comes out as a pair. When he comes out, I just say, well, he came out as a positive. and then with one y left in there. So you could write it like this. This is an okay way to write it. Or you could also write it as 2xy square root 3y. Either way you write it, either, this way is kind of messy looking with that double, but it means the same thing as this. And you can imagine that mathematicians like this better because there's fewer symbols. And believe it or not, and you're probably not going to believe this, we do like for things to look as simple as possible. It just doesn't seem that way whenever we're going through problems. And if you have any question on any of these, be sure and let me know. Just note that when you see this little disclaimer here, just put your absolute values on the outside, because what that means is the answer is going to be positive. All right, you guys know what to do. If you have any question, be sure and send me an email. Let me know how I can help you. And have a good day.